Example problem. Calculate the tension T in the cable which supports the 500 kilogram mass with the pulley arrangement shown here in this figure. Each pulley is free to rotate about its bearing, and the weights of all parts are small compared with the load. Find the magnitude of the total force on the bearing of the pulley C. Yeah. Solution. The free body diagram of each pulley is drawn in its relative position to the others. You can see here I have drawn the free body diagram for each part. This is the part C, let's say for the pulley C. And this is for the pulley B, and this one for the pulley A. Now you can see for the pulley A, I draw instead of the kilogram, 500 kilogram, that means this is the mass, I put it as a weight. Okay, there is a weight here. And when I cut in this section here, I will get there is a tension because we have here a loop. Okay, so I put here T1 and T2. When I move to the pulley B, and when I cut here, I will get this is T3 and T4, and due to I have T2 here, so this one is T2 as well. When I move to the pulley C, okay, I have pin connection and as we know, in the pin connection I need to put two forces, one parallel to the x-axis, one parallel to the y-axis. I have tension here, so I will put the tension, and due to the tension here in B is equal to T3, so the same tension in the pulley C, okay, called T3. Now we begin with the pulley A. Let's start with the pulley A, which includes only known force. Why I start with pulley A? Because it has, or it includes, the only known force. For all this figure I have just the force of the mass here. With the unspecified pulley radius designated by R. So I don't know what is the radius of these pulleys, so I specified as or designed by R. I will put the radius for each pulley is equal to the equilibrium of moments about its center O, okay, and the equilibrium of forces in the vertical direction required. So here I will take the moments about O, and the summation of the vertical forces equal to 0. Again, the moments about O is equal to 0, and the forces in the direction of Y is equal to 0. And the moment about O, now it is T1 multiplied by the radius, okay, in this direction. So in that direction will be minus T2 multiplied by R equal to 0. In that case, T1 is equal to T2. T1 is equal to T2. Now if I take the summation of all forces in the y direction equal to 0, so T1 plus T2 upward minus 500 multiplied by 9.81 equal to 0. So I can get T1. So this is T1. And T1 equal to T2. So T1 equal to T2 equal to 2450 Newton. So now we can see T1 is equal to T2. From the example of pulley A, we may write the equilibrium of forces on pulley B by inspection. Now from the pulley A, I can conclude that T3 equal to T4, T3 equal to T4, and T3 equal to T4 and equal to T2 over 2, T2 over 2. This is the conclusion from the example of pulley A. Why? Because now you can see T2 to T1, that means T1 plus T2 equal to that. Here that means T3 plus T4 is equal to T2. Now, so again T3 is equal to T4 and T3 equal to T4 equal to T2 over 2. Now, for pulley C, if we move for pulley C, the angle is equal to 30. The angle of the T with respect to x-axis is equal 30. In no way affects the moment of T about the center of the pulley, so that the moment of equilibrium requires T T is equal to 1 minute please. Now you can see here, so that the moment equilibrium here, T is equal to T3. T, this one, equal to T3, or T is equal to 1226. So now T is equal to T3. T is equal to T3. Okay, so this one is equal to that. Again, for pulley C, we can conclude that T is equal to T3. Why? Because I have the same cable. Now, equilibrium of the pulley in the x and y direction requires. Now, if we do the equilibrium here, again, I have the value of T is equal to T3. I have T3, so if I take the equilibrium for the C, I can get Fx and Fy. Now, summation of all forces in the x-axis is equal to 0. I have the value of T, it is equal to 1226 cosine theta positive. So this tension cosine theta positive, minus that, minus Fx, so I can get Fx. I have one equation, one unknown, so I can get Fx. If I take the summation of all forces in the y direction equal to 0, so T sine theta upward minus T3, this is upward, this is T3 downward, plus Fy equal to 0. So I can get Fy. So the resultant of the two forces, these two forces is equal under square root Fx square plus Fy square. F is equal under square root, this is Fx square, this is Fy square, and we can get the total is equal to 1226 Newton. Sample problem number 2. The uniform 100 kilogram beam, I-beam here, is supported initially by its end ruler on the horizontal surface at A and B. So here this is I-beam supported at ruler here A and B. By means of the cable at C, I have a cable here at C, it is desired to elevate end B to position 3 meters above the end of B. Now I need to elevate, okay, B, the end B to position 3 meters above A. 3 meters above A. Now determine the required tension P and the reaction at A and the angle made the beam with the horizontal in the elevated position, and what the angle here. So if we draw the free body diagram here, now we note the reaction on the ruler A. Now you can see I have, when I pull here, the B will be at altitude is equal to 3 meters. So I have a ruler here, so I have one force, and the weight, do not forget the weight in the middle, of the beam, vertically downward, and I have the force at C is equal to P. Now if I take the moment equilibrium about A, so I have two forces. Okay, now you can see P, this P, I have this angle is equal, the angle here it is unknown, P multiply by this, now P, and multiply by this dimension, not that, by this dimension, so it is 6 cosine theta. So P multiplied by D is equal to 6 cosine theta minus 100 multiplied by 8.9 multiplied by 4 cosine theta, So I can eliminate cosine theta, I can get the force P. This is the first answer. Now the equilibrium of the vertical forces. Now I will take the equilibrium for summation of all forces in the y direction is equal to 0. I have this is in the y direction, so it is 654 upward, minus r, why? Because r is plus r, because r in the same direction of P, minus the weight, so I can get the r, that's mean the reaction at point A. Now I need to get the angle theta, the angle actually I can find it easily because I have here sine theta is equal to 3 over 8. I can get theta. So theta is so easy, I have 3, and this is A, so 3 over, that's be the opposite over the hypotenuse, so I can get the angle theta. The sample problem 3. Now determine the tension T, or the magnitude T of the tension in the supporting cable. Now what is the tension in this cable, and the magnitude of the force and the magnitude of the force on the pin at A for the jib crane shown. Now what is the forces here? The beam AB, this is the beam AB, is standard 0.5 meter, this is the 0.5 meter IB, 0.5 meter IB, with the mass is equal to 95 kilogram per meter of the length. 95 kilogram per meter of the length. Now, first of all, the system of symmetrical about the vertical XY plane through the center of the beam. So, the problem may be analyzed as equilibrium of coplanar force system. The free body diagram of the beam is shown in the figure with the pin reaction at A represented in terms of two rectangular components. Now you can see this is the free body diagram of the figure. I have tension here, I have tension, I have force is equal to 10 kilogram. Okay, 10 kilogram, and the distance here, the distance in the middle is 0.5, as he said here, 0.5 I beam. And due to I have pin connection here at a pin connection, so I will put two forces. Do not forget, this is the x-axis, this is the y-axis. Again, this is the free body diagram with all the forces that I need to solve. The weight of the beam, now I have 95, okay, 95 multiplied by 95 kilogram, okay, multiply by 95 kilogram, multiply by 5, multiply by g, this is g, it is equal to 4066 Newton, or it is equal to 4.66 kilonewton. There is no difference, and acts in the center. Do not forget, because I have beam, and always we said that weight always in the middle of the body. Now I have here I have three unknowns, ax, ay, and t. So this is unknown, this is unknown, and this is unknown. Now we begin with the moment about point A. Okay, now to determine the unknowns t and ay and ax, first of all I will take the moment about A, the moment about A. Why? To eliminate ax and ay. To eliminate ax and y. To eliminate ax and y. In that case, I can get t. I can get t. Now you can see here the summation of moment about A is equal the t cosine 25, cosine 20. So I will get a component here, multiply by 0.5. I multiply by 0.25. Why? Because the distance from this point to that point is equal to 0.5 meter. In the middle I have 0.25. So this component t cosine 25 multiplied by 0.25 meter, plus this is in this direction, counterclockwise, plus t sine 25, that's mean in this direction, multiply by the length of the beam. The length of the beam is equal to 5, minus this distance. Why? Because we are talking about the moment about A. Okay, about A. So the distance from A, okay, from A to B is equal to 5 minus this distance, minus 10. Okay, now I have this force minus 10, because this is downward, will makes a moment clockwise. 10 multiplied by 5 minus 1, 5, the length 5 minus 1.5 minus that, minus 4. Okay, this is this is the weight. Okay, now so you can see the weight, because I have a force and I have a weight. Okay, so the weight multiplied by the distance, it is equal to 5. Okay, 5 minus, okay, now the in the middle, this force is in the middle of the beam, so it is the force multiplied by 2.5 meter minus this distance equal to 0. In that case, I can get T. Now, I want to calculate AX and AY. Summation of all forces in the x-axis is equal to 0. Summation of all forces in the x-axis is equal to 0. So AX in the direction plus minus t cosine 25 equal to 0. Why? Because I have just two forces in the x-axis, AX and the component of t, in the x-axis. So I got AX. Now I need to find AY. So summation of all forces in the y direction equal to 0. I have this force, and the component of the t in the y direction. So AY plus the tension is equal to 19.61 multiplied by sine 25, this is upward, minus the weight downward, minus this force downward. So I can get AY. I will put AX under square root. I will get the resultant force in the point A. So you can see A is equal to under square root AX square plus AY square is equal to 18.880 kilonewton. That means this is the resultant reaction force, or the total force at point